Hello everyone, my name is Tanay Trivedi and I am pursuing my Masters in Construction Engineering and Management from CEPT University. My student code is PCM24411. As part of the second semester studio, Construction Project Execution, Monitoring and Control, we prepared a report including different aspects of construction and monitoring a corporate house. These included pre-construction, planning, quality management, material management, use of lean tools, contract administration, project scheduling and tracking, and earned value management. Out of these, my portfolio includes planning, work sampling, and the use of tools of quality. Firstly, a brief about the project. The corporate house is a commercial project located in an integrated township in Ahmedabad. The township offers a balanced blend of commercial and residential spaces to optimize work-life balance. It also supports businesses through high-quality infrastructure and amenities. The Greenfield project has two basements and ground plus 16 floors, with a site area of 12,637 square meter and a construction area of 76,995 square meter. The project estimate is 76 crores and an item rate contract is being utilized. The scope of work includes excavation, RCC, waterproofing and block masonry, while the estimated time of completion is 1.5 years. Shown in the map is the site area, labor colony and site office. Pour planning for the second floor roof slab was carried out. The built-up area of the floor was 3,184 square meter. As shown in the layout, the slab was bifurcated into three pours. Quantities for formwork, reinforcement, and concreting of columns, column caps, shear walls, flat slabs, and beam were calculated, and further rate analysis was carried out. All assumptions made for calculations were as per site details and condition. A schedule was prepared for the project on MS Project. 4.1 includes the core area having shear walls and staircases and having an area of 311 square meter. And as seen in the shuttering movement plan, 4.1 has Cosmos type of formwork. 4.2 had flat slabs, columns and beams on the periphery, having an area of 774 square meter, with the flat slabs utilizing MEWA formwork, columns MSPD, and beams and column caps utilizing conventional plywood. 4.3 had the same elements and types of formwork and an area of 1,154 square meter. The cumulative cost of formwork for all three pours is shown in the table. So the unit rate calculations were carried out as per site conditions and repetitions for each type of formwork. The unit rate is inclusive of all elements required in the shuttering system. For example, for conventional formwork, plywood, Tata box, runner putty, and props were considered. The unit rate calculations included all elements and their corresponding cost per unit. In the table, the total quantity for each type of formwork is shown along with its unit rate cost and the total cost per floor. And the total cost per repetition which was considered for the final calculation came up to rupees 197 per square meter for conventional formwork, rupees 12,040 per square meter for MEWA, rupees 435 per square meter for MSPD formwork, and rupees 422 for Cosmos formwork. The productivity of labor for formwork came up to 0.39 meters square for man-hours. Next is reinforcement. So reinforcement calculations were carried out for all elements of the floor. The assumptions that were considered for calculations are as follows. The first is a floor height was of 3.6 meter was considered. Cover margins were taken as per site conditions. Bend deduction of minus D was taken for every 45 degrees. Lap length was taken as 50 D, which is as per drawings, and a wastage of 3% was taken as per contractual conditions. So based on the following assumptions, a bar bending schedule was prepared for the floor. For column, the quantity of steel came up to be 39.77 metric ton. For beam, 24.35 metric ton, which is due to the presence of the flat slab, so the beams are only present on the periphery. And for slab, it came up to be 44.13, which is due to the presence of 25 mm triple layered steel as shown in the table. The total quantity of steel for the floor was 109.39 metric ton. So including wastage, 113 metric ton of rebars are required for the floor. Couplers are used for rebars having dia of 16 mm or more, and the coefficient of reinforcement was calculated to be 35.77 kg per meter square. Tower crane and steel yard machineries which are bar bending, cutting and threading machines were considered for owning and operating cost. And shown in the graph is the monthly requirement of steel in 2025, and as seen, the peak is in May 2025. Next is concreting. Concreting of M40 for slabs and M55 for columns happens on site through a stationary boom placer. The location of the boom placer is shown in the concreting plan in blue, and a concrete pump and pipeline are available on site. The concrete pump is placed near the main gate as shown in red in the concreting plan. So the quantity of concrete for each element was calculated, and for columns it is 593 meter cube, for beam it is 98.14 meter cube, and for slab and column cap it is 215.59 meter cube, and the total concrete quantity required for the floor is 905 meter cube. On the top right is the total cost of construction for the floor, which is calculated for each element, that is formwork, reinforcement, and concreting. And the cost includes material, labor, owning and operating, and others. Other includes tax and contingencies. So total cost for formwork came up to be 41.6 lakhs, for reinforcement 109 lakhs, and for concreting 66.1 lakhs. And the percentage of concrete and reinforcement for the floor is 30 and 50% respectively, and for formwork it is 20%, mainly due to the material of formwork being non-perishable, and repetitions were utilized for the calculations. Next is the tool of quality. We established control limits for compressive strain test of concrete of M40, which is used in slabs. The result of compressive strain tests were taken from the on-site cube register, and one sample set contained 3 observations of compressive strength of cubes. The table shows the X bar, which is the mean of compressive strength, and the value was 48.65 kilonewton per meter square. R bar was the mean of range, which was 3.32 kilonewton per meter square, and R bar is the difference in compressive strength of observations within one set. The constants are also shown in the table along with the upper and lower control limits which we calculated for compressive strength as well as range. The highest standard deviation limits are also shown, which are plus and minus 15%. So X bar is the mean of values of compressive strength, and it indicates the average compressive strength. 36 sets were considered, so there was 36 observations in total, and each set had three observations. The graph represents the variation in results with respect to the calculated and highest control limits. So the straight lines are the upper control limits. The second one is the average, which was 48.65, which is X bar. And variation of the results is shown in the graph, with the lowest observation coming up to be 44.01 kilonewton per meter square, and the highest one coming up to be 53.41 kilonewton per meter square, which are all well above the desired compressive strength for M40 grade of concrete. R bar is the variation of compressive strength of each set, that is the difference of value within a set of 3. It can be helpful to identify results with extreme outliers. If the variation is high, then the set can be discarded as the average value will be skewed. As seen in the graphical representation, there are two samples, sample number 6 and 11, which are outside the upper control limit, which shows that within the set, there is a large variation in compressive strength. So it is recommended that the set isn't considered. An Ishikawa diagram was prepared for a non-conformity identified on site, which is honeycombing of a shear wall. The causes for the non-conformity were identified, and the root causes for the problem were poor workability of concrete, haphazard work, lack of tamping, and not using proper equipment, that is not enough vibration, not enough using of needle vibrator. A Pareto chart was prepared for the non-conformities and cost of rework. So non-conformity reports are submitted on a monthly basis by the client to the contractor. And after bifurcating all the non-conformities through 6 months of NC reports, a Pareto chart was prepared to identify the highest occurring non-conformities and their corresponding cost. So as seen in the chart, the top two non-conformities are mainly honeycombing and stacking of steel, and the cost for rework is mainly in honeycombing. So it shows that over 80% of the cost incurred is due to the main non-conformities. So work sampling is a lean technique used to prepare a statistical sample of how much time workers are allocating to activities. The methodology followed for tour-based work sampling was firstly the characterizing of the area which was to be observed. Second is categorization of activities in the tour. Third is identification of the route which was to be followed. Then there was preparation of data sheet and collections of samples and analysis of those samples. So the activities were bifurcated into value adding, non-value adding, and non-value adding but necessary tasks. Tours were performed every 30 minutes through a fixed route. The fixed route is shown in a 3D spaghetti diagram, which shows that the tour started at position 1, which is the entry of the site. Position 1 was the steel stacking yard where steel was stored. Position 2 was cutting and bending yard. Position 3 was the shuttering yard for maintenance of formwork. Fourth was the area of block work, while fifth was the area of shuttering. Position 6 and 7 show the show the place where reinforcement work was going on the second and third floor. Position 8 is where formwork and slab cleaning was going on the third floor, and the tour ends at position 9, which was reinforcement at the fourth floor. Tours were performed every 30 minutes, and 16 observations were made for 2 days. Observations were taken from 9 a.m. to 6 p.m. with a lunch break from 1 to 2 p.m. The tasks that were observed were reinforcement, formwork, block work, and miscellaneous works. And the sub-activities of each of those tasks were allocated into value adding, non-value adding, and non-value adding but necessary. All observations taken are in labor count, and observation for both days for the analysis has been added. The labor count for 11th was 152 and for 12th was 165. The graph on the bottom right shows the comparison of activities, which is the comparison of VA, NVAN, and NVA for both days. The table shows the observations of labor counts for each tour that happened every 30 minutes. So for example, from 9 to 9:30, we observed 128 laborers performing value adding activities, 44 performing non-value adding activities, and 50 performing non-value adding but necessary activities. And the frequency distribution of observation shows the time ranges where workers were performing most value adding and as well as the least value adding. So the red highlight shows the time of 2 to 3 where the least value adding activities were being performed and NVA was higher. And the green highlight shows the time where most value adding activities were being performed. We carried out time-based, activity-based, and location-based analysis for our observations. So for time-based analysis, we bifurcated the observations into 3 time periods, which were 9 to 11, 11 to 4, and 4 to 6. And as seen in the graphical representation, we prepared a graph of samples per minute as the due to the time difference and time intervals of all 3 slots. And the graph shows that the third time period of 4 to 6 has the highest value adding activities where as the workers have to finish their assigned tasks by 7 p.m. so they are rushing to finish work. NVAN is higher in the first time slot of 9 to 11 as it includes time for mobilization of tools and materials, while NVA is highest during the slot of 11 to 4, which coincides with the lunch break as workers return late and are working leisurely. The activity-based analysis shows the bifurcation of VA, NVA, and NVN for each activity we observe. Formwork and reinforcement have a similar spread of VA, while the key difference is NVA, with reinforcement having less NVA due to it being critical to the casting of slab and as it has more supervision. And the pie chart shows the bifurcation of value adding, non-value adding, and NVAN. The location-based analysis for reinforcement was done for the bar bending yard, reinforcement on the second floor and the third floor. Higher observations in value adding were on the slab due to the urgency of work, and the bar bending had a higher NVA with a lot of observations of idling in the bar bending yard. So last is the conclusion. For core planning, we prepared a schedule for the project on MS project as per actual site holidays and working hours. The schedule was used for duration of activities. Finding quantities of all of these major activities helps with ordering and material management as well as smooth execution on site. Labor productivity of each activity was calculated. For formwork, it came up to be 0.39 meter square per man days. For reinforcement, 0.11 metric ton per man days. And for concreting, it was 2.84 and 1.35 meter cube per man days, respectively, for slabs and columns. The cost of construction for the floor came up to be 2 crores 15 lakhs, out of which reinforcement had the highest weightage of around 50% of the cost. The reinforcement to concrete ratio was calculated to be 125.74 kg per meter cube, and the coefficient of reinforcement was calculated as 35.77 kg per meter square, while the coefficient of concrete was 0.28 meter cube per meter square. For tools of quality, we identified UCL and NCL through which we were able to identify anomalies in the compressive strength testing. The chart for X bar, however, did not show any anomalies as all of the observations were within acceptable limit as per IS code as well as calculations. However, few results were above the upper control limit, which generally does not cause problems. However, it may cause problems due to higher rate of hydration due to the higher compressive strength. The R bar chart shows that two samples were lying outside the desired limit. This shows an extreme difference in the strength of the same set of samples, indicating a skewed average. So that means one of the result had a very low strength while one had very high, which balanced out the average. However, the singular observations had a problem. So those observations were advised to be discarded. And through control charts, we gauged that the highest cost for non-conformities on site was due to honeycombing, as it has it as it as it had the highest number of observations of highest number of reports as well as the highest cost. For work sampling, we performed work sampling for 2 days and created a database of observations of labor counts to account for activities which added value and those which did not. By creating the sample of observations, we were able to identify activities which were non-value adding. We performed location, time, and activity based analysis. From time-based analysis, we were able to analyze where labor performed, in which time slot labor performed more value-adding and performed more non-value-adding. Location showed that due to the supervision of staff on slab, reinforcement had higher number of observations on the slab for value-adding activities than for non-value-adding activities. And the frequency distribution showed a number of absent labor, as the total labor count was 152 and 165 for both days. However, the average observations were 111 and 117. Further use of work sampling for a larger time period would create more accurate results. However, utilizing more lean tools with work sampling can be beneficial for reducing time and improving efficiency.